Hello students, welcome to today's lecture. So in today's class we will explore mathematics, probability and CRT section 13.1, 13.2, 13.2.1. So let's start. This is disclaimer. So we will start our discussion on probability focusing on basics first. This is called introduction, right? And it sets the stage for understanding how likely different events are to happen. Then we will move to conditional probability. Next we will definition. We will study definition for 1. Conditional probability is written as probability of A upon B, right? After that, next, we will look at the properties of conditional probability. These helps us to understand how conditional probability behaves and how can we use it in different situations, right? Then we will focus on properties 1 to 3. We will solve example 1 to 3 and see these ideas in action, okay? So let's see. Let's start. Let's start by understanding what a random experiment is. In probability, a random experiment is any process where the outcome cannot be predicted with certainty. Even if we repeat it, repeat it under the same conditions, right? Even if we repeat it under the same conditions, right? Then we talk about the sample space, which we usually call S. The sample space is simply the set of all possible outcomes for a random experiment. For example, if we toss a coin, the sample space is heads and tails. If you roll a six-sided die, the sample space is the numbers 1 to 6. It's important to clearly define the sample space before we start calculating probabilities. Next, we will introduce the concept of an event, which we label as E. An event is any subset of sample space, right? Now we will look at the axiomatic approach to probability. This approach gives us a formal way to assign a probability value to any event E. The probability, written as probability of E, is a number that tells us how likely the event is to happen. We will see the rules that this probability must follow. So the first rule is that the probability of any event E must be between 0 to 1, including 0 and 1. That means 0 is less than or equal to probability of E and probability of E is less than or equal to 1, right? The second rule says that the probability of the entire sample space S is always less than 1, right? Always 1 actually. Probability of sample space S is always equal to 1. The third rule deals with the mutually exclusive event, which means events that cannot happen at the same time. If E and F are mutually exclusive, then probability of either E or F happening is just the sum of their individual probabilities. Therefore, probability of E union F is equal to probability of E plus probability of F, right? Okay. Now, let's start by talking about the probability of an event. In mathematics, the probability helps us predict how likely an event is to happen, especially when dealing with experiments or random processes. Now let's define what we mean by an event. An event, which we usually call E, is just a subset of the sample space S. Sample space S includes all possible outcomes of an experiment. For example, if we toss a coin, S would be heads and tails, and an event E could be getting a head. So probability of E will be equal to number of outcomes favorable to E upon total number of outcomes, right? We can say probability of E will be equal to number of outcomes favorable to E upon total number of outcomes, okay? And we can also write this formula as probability of E is equal to number of E divided by the number of S, right? Where number of E is the number of outcomes in event E and number of S is the number of outcomes in the sample space S. Both NE and NS are just counts, so they have no units, right? You can notice that as NE increases, the probability goes up, and as NS increases, the probability goes down if NE stays the same, right? Now let's look at the addition rule for probability. If we have two events, E and F, the probability that either E or F happens is probability of E plus probability of F minus probability of E intersection F, right? Now complementary events. The the complement of event E is written as E dash, right? Which is basically E complement. Is everything in the sample space that is not in E. So probability of E complement is basically 1 minus probability of E, right? Probability of E complement is basically 1 minus probability of E, right? Now let's see conditional probability, which is a key concept in probability and statistics. This is especially important in physics when we want to predict the likelihood of an event, given that something else has already happened, right? Let's start by understanding what this means and why it's useful. So conditional probability is the likelihood of an event occurring given that the event has already occurred, right? Given that the event has already occurred. Okay. Especially if we have two events E and F, which are part of the same sample space S, the conditional probability of E given F is expressed as probability of E upon F, right? Okay. Now let's look at the formula for conditional probability. Let E and F be two events associated with the same sample space S of a random experiment. So we can say the conditional probability of the event E given that F has occurred divided by probability of E upon F is given by probability of E upon F is equal to probability of E intersection F upon probability of E F. This formula holds true provided that probability of F not equal to 0, right? We can say that probability of F should not be equal to 0, right? Example, a die is thrown, let E be the event, which is a number 4 appears, and F be the event, which is the number is even. We have to find probability of E upon F, right? We have to find probability of E upon F. Okay. Let's look at the solution part. So first let's define our sample space and events involved. The sample space is just all the possible outcomes when we throw a dice, and the events E and F are specific results we are interested in. Okay. So sample space S is basically 1, 2, 3, 4, 5, 6. Event E is equal to 4 because number 4 appears is event E. Event F is basically 2, 4, 6. Intersection of E and F is basically E intersection F, which is 4, right? Now let's calculate the probabilities. On calculating the probability of event F, we can say probability of F will be equal to number of event F upon number of S, right? Which is equal to 3 upon 6, right? Which is equal to 1 upon 2, right? 1 upon 2. Okay. Now on calculating the probability of the intersection E intersection F, probability of E intersection F will be equal to number of E intersection F upon number of S, which is equal to 1 by 6. Now on applying the conditional probability formula to find probability of E upon F, we get probability of E upon F will be equal to probability of E intersection F upon probability of F, which is equal to 1 upon 6 upon 1 upon 2, which is equal to 1 upon 3, right? Thus the conditional probability of E upon F is basically 1 upon 3, right? We can say that probability of E upon F is basically 1 upon 3, right? Okay. Next is NCERT section 13.2.1 properties of conditional probability. So we are going to discuss an important property of conditional probability, specifically its range. So property 1 is basically range of conditional probability. Let E and F be events of sample space S. So probability of E upon F satisfies the conditions of a probability. Okay. Therefore, probability of S upon F is basically equal to 1. Probability of E upon F is greater than equal to 0. Let's see proof. We know that probability of S upon F is equal to probability of S intersection F upon probability of F. Since F is a subset of S, so we can say that S intersection F is basically equal to F. Therefore, we can say that probability of S upon F is basically probability of F upon probability of F, which is equal to 1. Second, since probability of E upon F is basically probability of E intersection F, which is equal to probability of E intersection F upon probability of F. And probability of E intersection F greater than equal to 0, since it's a probability, and probability of F greater than 0 by the definition of conditional probability when probability of F equal to 0, right? Probability of F equal to 0. So it's clear that probability of F is not equal to 0 basically, right? So it's clear that probability of E upon probability of F is basically greater than equal to 0. We can say that probability of E upon probability of F is greater than equal to 0, right? Next is property 2, addition rule for conditional probability. This rule helps us find the probability of either event A or event B happening, right? Given that another event F has already occurred. So if A and B are any two events of a sample space S and F is an event such that probability of F should not be equal to 0, then we can say that probability of A union B upon F is equal to probability of A upon F plus probability of B upon F minus probability of A intersection B upon F. Okay. So let's see proof of this. So we know that for any event X and F with probability of F not equal to 0, the conditional probability is defined as probability of X upon F should be equal to probability of X intersection F upon probability of F. So on substituting the expression for conditional probabilities using the definition, we can say probability of A union B upon F is basically equal to probability of A union B intersection F upon probability of F. So we can say that probability of A upon F will be equal to probability of A intersection F upon probability of F, right? And probability of B upon F is equal to probability of B intersection of F upon probability of F. Okay, right? So we can say that if A and B are any two events of a sample space S and F is an event such that probability of F not equal to 0, then probability of A union B upon F will be equal to probability of A upon F plus probability of B upon F minus probability of A intersection B upon F, right? So we were proving this. So we can say that probability of A intersection B upon F will be equal to probability of A intersection B intersection F upon probability of F. So according to the basic properties of probability, specifically the inclusion exclusion principle, we have probability of A union B intersection F will be equal to probability of A intersection F union B intersection F, and it will be equal to probability of A intersection F plus probability of B intersection F minus probability of A intersection B intersection F, right? Thus we can say that probability of A union B intersection F upon probability of F will be equal to probability of A intersection F plus probability of B intersection F minus probability of A intersection B intersection F upon probability of F, right? So this simplifies to probability of A intersection F upon probability of F plus probability of B intersection F upon probability of F minus probability of A intersection B intersection F upon probability of F, right? Now substituting back the expression for the conditional probabilities, we have probability of A union B upon F will be equal to probability of A upon F plus probability of B upon F minus probability of A intersection B upon F, right? Hence we can say that it is proved, right? Okay. Now let's see some special case, which is if A and B are disjoint events, that means A intersection B is equal to phi. Then probability of A union B upon F will be equal to probability of A upon F plus probability of B upon F, right? Since A intersection B is equal to phi. Now property 3, complement rule for conditional probability. We can say that probability of E complement upon F will be equal to 1 minus probability of E upon F, right? Let's see proof of this. Given that probability of S upon F will be is equal to 1, we can express the event S as union E union E complement, right? Where E complement is the complement of E, right? Therefore, we have probability of E union E complement upon F will be equal to 1. Since E and E complement are disjoint events, we can use the additive property of probabilities to state that probability of E upon F plus probability of E complement upon F will be equal to probability of E union E complement upon F, which is equal to 1, right? Now, rearranging this equation gives us the relationship, which is probability of E complement upon F is equal to 1 minus probability of E upon F, right? This provides the conditional probability of the complement event given F, right? Got it? Now let's see NCERT section 13.2 example 1, which says if probability of A is equal to 7 upon 13, probability of B is equal to 9 upon 13, and probability of A intersection B is equal to 4 upon 13, then we have to evaluate probability of A upon B, right? We have to evaluate probability of A upon B, right? So let's see how can we evaluate probability of A upon B. So the conditional probability of A upon B represents the probability of event A occurring given that event B has already occurred. So it is calculated using the formula, which is probability of A upon B is equal to probability of A intersection B upon probability of B. Now we have probability of A intersection B is equal to 4 upon 13. So the probability that both the events E and B occur, right? A and B occur. Now probability of B is equal to 9 upon 13, which is the probability that event B occurs. Got it? So substituting these values into the formula we give, formula gives probability of A upon B will be equal to 4 upon 13 upon 9 upon 13, which is equal to 4 upon 9. Thus the conditional probability of A given B as probability of A upon B is basically 4 upon 9, right? We can say that probability of A upon B is basically equal to 4 upon 9, right? Next example, NCERT section 13.2 example 2, which says a family has 2 children. What is the probability that both the children are boys given that at least one of them is a boy, right? Given that at least one of them is a boy, right? Let's see how can we solve this. Let B stands for a boy and G for girl, right? So sample space of the experiment is basically S, which is BB, GB, BG, and GG. Right. Let E and F denote the following events. E, both the children are boys. F, at least one of the child is a boy. Then event E is basically BB and F is basically BB, GB, BG. Right. Now E intersection F will be equal to event BB. Okay. Thus probability of F will be equal to 3 upon 4 and probability of E intersection F will be equal to 1 upon 4, right? Therefore, we can say that probability of E upon F will be equal to probability of E intersection F upon probability of F, which is equal to 1 upon 4 upon 3 upon 4, which is equal to 1 upon 3, right? Which will be equal to 1 upon 3, right? So 1 upon 3 is basically the right answer, okay? Now, next one is NCERT section 13.2 example 3, which is 10 cards numbered 1 to 10 are placed in a box, mixed up thoroughly, and then one card is drawn randomly. If it is known that the number on the drawn card is more than 3, what is the probability that it is an even number, right? We have to find the probability that it is an even number. Okay, so let's see the solution part. Let's start the solution. The conditional probability of A upon B represents the probability of event A occurring given that event B has already occurred. It is calculated using the formula, which is probability of A upon B is equal to probability of A upon probability of A intersection B upon probability of B. Let A be the event, the number on the card drawn is even, and B be the event, the number on the card drawn is greater than 3. So we have to find basically probability of A upon B. Okay, right? Now the sample space of the experiment is basically S is basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then event E is basically 2, 4, 6, 8, 10, and event B is basically 4, 5, 6, 7, 8, 9, 10. Then A intersection B will be equal to 4, 6, 8, 10. Also, probability of A will be equal to 5 upon 10, probability of B is equal to 7 upon 10, and probability of A intersection B is equal to 4 upon 10. Then we can say that probability of A upon B will be equal to probability of A intersection B upon probability of B, which is equal to 4 upon 10 upon 7 upon 10, which after simplification will be equal to 4 upon 7. Clear? So the correct answer of the given example is 4 upon 7, right? Got it? So thank you for your attention. I hope this lesson was helpful to you all, right? Thank you so much.